Welcome, class, to a workshop on Coach Joe rules. In this lesson, we will review Coach Joe rule number 2, which states, utilize the 3 laws of TDD. Traditional development involves writing the code first, then later, create the supporting tests. Test-driven development is a style of programming where the test is written first, then implementation code. By writing the test first, you can prove the implementation behavior works as expected. This includes accounting for things that can go wrong, like validation checks, edge cases, and possible exceptions. One at a time, write one small test up front, then implement the code to make the test pass. This helps write a well-designed application with clean quality code. The small step approach provides quicker feedback and allows for easier refactoring. A common approach is to follow these steps: red, green, refactor. In the red step, write a test that fails. It is important to see the test fail first. In the green step, write enough code to make the test pass. In the refactor step, optional changes to the test or implementation code can be made. Just make sure the test still passes after any changes. After completing the refactor step, start over with the red step and begin the next small change by writing a failing test. Repeat this process over and over until the small coding feature is completed. Uncle Bob summarized this with the 3 laws of TDD. Let's build a simple calculator example to illustrate the steps. In the red step, create a class file to hold some supporting tests. Next, write enough of a test to get it to fail. A compiler error creating the calculator object is considered a failing test. In the green step, create the calculator class file. The test no longer has a compiler error and is considered passing, even though there is no assert statement yet. In the refactor step, we can clean up the test code or implementation code. Right now we don't have much, so let's keep working. In the red step, let's add an assert statement to prove the object exists. The test should pass. Let's run it. And it does pass. In the green step, there is nothing to do. In the refactor step, let's update the test name. The test should still pass. Let's do a little more by returning to the red step. Create a new test to prove the add method returns a default value like 0. The test is failing with a compiler error. In the green step, create a new add method to the class. Notice no parameters were supplied in the test or code. We are only trying to prove the add method exists, not a fully completed code block. The initial method should return a default value like null, empty string, or in this case, a 0. If we run the test, it now passes. In the refactor step, I don't see anything major to clean up yet. Let's add one more small action in the red step. Let's pass in 2 parameters. Now the test has a compiler error. Moving to the green step, we can add 2 parameters to the method signature. The compiler error has been resolved in the test, and it passes. No refactoring is needed. In the red step, let's change the assert to expect 7 if the add method has parameters of 2 and 5. The test fails. In the green step, replace the 0 with some implementation code. The test should now pass. No change is needed in the refactor step. Back to the red step, let's add a new test for subtraction. Let's create the calculator object, which we know already exists. Let's assert a 0 parameter subtract method that returns a default 0 value. The test is failing with a compiler error. In the green step, create a 0 parameter subtract method. Inside the code block, just return a default value of 0. The compiler error has been resolved in the test and it should pass. In the refactor step, you probably notice some duplicate code. The create calculator object now appears in 3 tests. Because these tests are passing, we can refactor with confidence. Add enough code to support a before each test setup. Next, create a private calculator property and set the value for all tests. After this small refactor, the tests still pass. In the red step, let's add two parameters of 7 and 5 to the subtract method. The test has a compiler error. In the green step, add the two parameters. The compiler error has been resolved in the test, and it passes. No refactoring is needed. In the red step, let's change the assert to expect 2 instead of 0. The test now fails. In the green step, replace the return 0 with some implementation code. The test should now pass. In the refactor step, no action is needed. These iterative steps will continue for multiply and divide. The idea is, use a test to drive your application development. The test and the code should work in tandem to create the application. Imagine there are two movers. The first one is called test, and the second one is called code. They will work together to move furniture, which represents an application feature. Each piece of furniture has its own unique challenges, just like each application feature. The movers will have more success if they both take small steps together. If one mover gets ahead while the other mover lags behind, the quality of work can suffer. The same is true for the application code. Prepare a few good tests to prove the behavior of this small feature works. By repeating this process over and over, everyone will have confidence in the finished product. Here are some common benefits and pitfalls when using the TDD approach. For starters, developers benefit when they focus on one small feature change at a time. Some important skills to acquire are writing a unit test before writing the code, and only writing enough code to make the test pass. Also, anything that goes wrong is easy to identify when only small changes are made. One common pitfall are developers that forget to run the tests frequently. Tests are a form of documentation. They can be used by current or future team members to understand the process. Don't combine all the small steps into a single test. Don't write a complex test setup. Try to keep each test short, simple, and easy to read. By taking small steps with test writing and code implementation, you begin to focus on better design. Interfaces are used which help decouple code and make testing easier. The result is a higher quality product with cleaner code and fewer bugs. The only downside is you may end up writing more test code than application code. When adopting the TDD style of programming, developers communicate better, become more productive, and are generally happier. Opponents of TDD often question how can writing useless tests with no asserts meet deployment deadlines and create a high-quality product. Sure, this iterative red-green refactor process appears to produce good results. The overall process has room for improvement. While the code is easier to read, modify, and maintain by any developer, some claim that too much time is wasted during the refactor step because many tests break. It is also true that TDD will have an upfront overhead cost, but will reduce time, effort, and defects in the end. Some will complain that TDD teaches bad coding habits by intentionally writing compiler errors in a test only to write out incomplete code next. This sounds problematic, borderline unprofessional, and breaks many Coach Joe rules. There are times when TDD is not needed and times when it should be utilized. Proof of concept projects, personal, or quick-to-market applications might not need TDD. Time is of the essence. As the project gains more attention from management and customers, the TDD approach becomes more appropriate. Because tests and code are written together, this helps write a well-designed app with clean quality code. It should be flexible, easy to maintain, and easy to test. With that being said, developers new to TDD would benefit from the small step-by-step process while gaining experience with certain design aspects. Just like learning to tie your shoes, ride a bike, or bake cookies, it will take a little time and repetition to acquire the skill. TDD is no different. As time goes on, you will begin to see the bigger macroscopic design picture repeating itself over and over again. Like building a class with properties, constructors, getters, and setters. Utilizing interfaces and dependency injection allows for design flexibility while making testing easier. Other design patterns begin to emerge from this process, like the factory pattern, strategy pattern, and builder pattern. At some point, you begin to realize the small steps are important, but possibly too small. Do I have to follow the letter of the TDD law? Can I write several tests before the code? Can I write the code without the tests? I think I know what I'm doing. It may be true that you know what you're doing and you're not becoming a cowboy coder. Provided the spirit of TDD is being upheld, there are a few options you can consider. Can I minimize the writing of compiler errors by writing out a more complete test and implementation code? Sure, combining a sequence of red-green refactor steps into one larger step is fine, especially if you have done this before. Can several tests be written first knowing all the possible edge cases? Sure, these could be coded out tests or just pseudocode. Can the code be written first and then tests later? Sure, just remember tests and code go hand in hand. From the earlier example, don't let one mover get too far ahead of the other mover. With these liberties, only complete this small feature. Don't begin to design and code out other features in advance. Are tests required for every little thing? Simple things don't require as much testing focus like class existence, getters, setters, and other simple operations. 100% code coverage is a great goal. However, it is important to test the complex areas, things that can and have gone wrong from your experience. Focus on anything needing air traps, complex logic, conditions, formulas, calculations, and polymorphism. A getter and a setter is just getting or setting a property value, not much risk of anything going wrong. If a condition or calculation is added to the process, then the risk goes up and testing becomes more important. A complex decision should be fully tested, like in a chess application when determining if a king is allowed to castle. There should be many supporting tests to prevent anything from going wrong. When refactoring, why do many tests break? During a refactor, understand why tests break. If there was a design change, I would expect compiler errors and broken tests. This means the existing tests did their job, they identified an issue. Complete the refactor as planned. Later, have a retro topic on the design change made and learn how to prevent this issue in future stories. Sometimes a bad test was written and the refactor exposed the problem. This happens from time to time. We all make these little mistakes. If the refactor was an implementation change, normally few if any tests should break. This assumes the unit tests were testing the behavior expected, not dictating the exact implementation. This is a common problem that bears repeating. Test behavior, not implementation. For example, if you have a list of objects and need it filtered down by some criteria, don't write tests forcing the use of a do loop, public properties, or a public conditional check. When the implementation changes to a stream, linked query, or a list comprehension, all the tests will break. Test the behavior of the action and allow the developers to implement it any way they want. When it is changed in the future, few if any tests will break and the developers will have confidence their change works. It may take a little time and repetition to appreciate TDD, but in the end, the improved design helps write a better application with clean quality code and fewer defects. I challenge you to utilize the 3 laws of TDD. It has helped me with projects I've worked on. I hope it helps you as well. Leave a comment down below with your TDD experiences. Look for other helpful Coach Joe videos. Remember, future senior developers, make it work, prove it works, then make it better. Ready? Break!